So if someone makes collector based diode as forward biased and emitter based diode as reverse biased, to select the mode, active mode, it is selecting the active mode but reverse active mode, because the structure is not designed for this direction, right? So you still have collector based diode as forward biased and emitter based junction as current source, but because of the structure and doping differences, this active mode would not be as much affected as in this direction, right? So it's okay. Three terminals, user can connect in any way, right? So Evermore Mole said that your diode, your transistor can be replaced with this equivalent circuit. So if someone connects in this configuration, make this forward, this reverse, then this route will be followed. Emitter base diode is forward bias and collector base is becoming the current source. But if someone configure in the reverse active mode, the collector base diode is forward bias, not as much affected as this was, and the base emitter diode is reverse bias to collect the current, right? Become the current source. So, but this mode is not as much effective as this one. So this is the Evermore model. Please consider the directions of these diode and these uh, current sources in contrast with the NPN transistor. So as we said while introducing the schematic symbol of the PNP and NPN transistor, highest voltage, middle voltage, lowest voltage, highest voltage, middle voltage, smallest voltage at the bottom of the page. So these are the parameters: collector base voltage, base emitter voltage, collector to emitter voltage. But in PNP you would be having emitter base voltage, collect base collector voltage. Usually people said it collector base again, but it should be base to collector voltage, and VEC. Whatever you can write, but write with right polarity, it would be okay. So large signal model of NPN transistor in active mode for common emitter configuration can be drawn in this way, right? It seems to be similar to the small signal model, only a difference of this diode will be replaced with the small R pi, right? So we will discuss it later. But here you can see base to emitter junction diode is forward bias, collector base is becoming the current source, and now you have a early effect consideration R naught, right? So VCE dependence on IC, right? So this is your model, large signal model with early effect and for common emitter configuration. So this is the collector current. You can write in the form of beta IB, or you can write in the form of this thing, right? Similar with the case with the PNP transistor, but here please see it is flipped vertically upward, right? Emitter to base diode is forward bias, because this is P, this is N. Diode anode will be here, diode's cathode will be here. So this will be forward bias, then emitter to collector will be becoming a collector current. So same is the case here, right? But here is the direction is from collector to emitter. Now the direction is from emitter to collector. The same thing. Now you can see you would be having higher potential at emitter with respect to the collector. So then you would be having VEC instead of VCE, right? Here you have written the collector current as beta IB. So you can write in the form of emitter base, here base emitter, here emitter base voltage. Please draw it yourself. So the diode will be behaving in the similar fashion as for every VBE greater than the forward bias voltage, you would be having a high current to be expected at the collector. Remember when you apply the reverse biasing in at the collector to base junction, right? And the temperature dependency would be the same for PNP transistor, but you would be a difference here, VEB instead of VBE. This is for NPN, right? So please draw it again with for the PNP by writing here VEB. Everything would be the same, right? As we have drawn the common emitter characteristics curves, look likes to be these, not straight, a little tilted, early effect, VCE dependency on IC, right? For every VBE, you have a curve for increase in VCE, right? For PNP transistor, you can do the same thing, right? For common emitter characteristics, it means emitter will be the common, right? But polarity will be as required for the PNP transistor. So for common emitter, for characteristics curve, you have to make these junction as forward bias if you want to see the active region and other region as well. So this would be positive than this one. This would be positive than collector, right? So for every VEB, if you increase VEC, then you will get one curve for that VEB. Same is the case here. So where you will get the characteristics curve. So VEC is increasing, it means here you would be having VEC. What should be the, where should be the curve? What would be the value of IC? You can see IC now, the collector is the current leaving terminal, right? So you would be having your characteristics curves here, right? Here it would be VEC, right? So to make a resemblance between these two, I draw minus IC, right? Otherwise this would be in the fourth quadrant, right? So please make yourself understand for all these things. If you have any problem, please do contact me. At the converse, it would be more better so that your question can be readable for others if they have any question in their mind. So if you remember the common base characteristics of an NPN transistor, you remember it is in the second, start from the second quadrant and goes to the first quadrant, right? Remains in the reverse forward region, the emitter base junction and the collector base junction. So it shows its saturation region here for common base, right? And from zero point 0.4 minus 0.4 to over to VCC, it remains in the active region, right? Whereas here from 0 to 0.3, because VCE is 0.3, at VC 0.3 your collector base junction becomes reverse bias. So you have actually visualized the active region here. So what would be the common base characteristics curve for a PNP transistor? Please think of yourself. I just tell you it will be starting from the fourth quadrant and it will be going towards the third quadrant. So let's see some difference between NP and PNP transistors. Symbolic representation you already saw, right? NPN, PNP, right? Majority carriers are electron in NPN transistor and holes in PNP transistor. Direction of electron current from collector to emitter. Here it is from emitter to collector. Minority carriers are holes. Obviously, if these are the majority carriers, then contrast would be the minority carriers. Mobility of majority carriers is high in NPN, whereas it is low in PNP because here electron moves the majority carriers from the emitter emitting is the electron are the electrons basically, right? So their mobility will be high. That's why NPN transistor is very fast than the PNP transistor, right? Because here hole moves and hole actually attracts the electrons. The movement of electron because of the holes is the hole current, right? So that's why this current is high. So conductivity level is high in this transistor, the NPN transistor, as compared to the PNP transistor. So it means the frequency response is also very fast for NPN, whereas comparatively low compared to the NPN transistor in PNP transistor, right? So how about the biasing schemes? It would be the same for NPN as we studied for the NPN, right? But remember, you have to make your VEB as forward bias, not the VBE. Emitter would be higher than base to have forward emitter base junction, and collector would be lower than base to have reverse collector base junction, right? For example, this circuit, if you want to have its DC equivalent circuit, remove the capacitors, open circuit it, you will get this DC circuit, right? So for example, if you consider that this transistor is operating in active region, then it means you would be having VEB is equal to 0.7, right? So if VEB is 0.7 and VB base voltage is 0, then how about VE? VE will be 0.7 higher than base. So it means here you will be having 0.7 volts, right? So now it is easy to find the current here. 10 minus 0.7 divided by this is your current, and this current is nothing but your emitter current, right? And if you have a beta, you can find the alpha, and alpha multiplied by this emitter current will be your collector current. If alpha is not given, you can take collector current same as the emitter current, because collector current is almost same to the emitter current, because you have very low base current, right? So it's up to you. They use alpha, that's why they have collector current small, lightly different than the emitter current, right? So now if you have this current, you can multiply this with this one, right? So this will be the voltage here, and when you add this voltage with this one, right, to get this voltage is minus 5 point. Please compute it yourself, right? So all the terminal voltages and currents have been found. Now for AC analysis, short circuit the capacitors and short circuit the DC sources to ground to get a ground here, a ground here, a short circuit here, a short circuit here, right? So, and replace your transistor with which model? T model, because you have something connected at the emitter, right? Actually, your input is connected at the emitter. This is a common base transistor, right? Common base, because you are giving your input to the emitter and collecting the output at the collector, right? So replace this transistor with the T model. Forget about the early effect, the R naught is neglected here. Then connect the base to ground, connect the emitter to the input, and emitter with the RE and ground, emitter with the RE and ground and input. How about the collector? RC to ground and to the output, RC to ground and to the output, right? So now you can find the input resistance and you can find the gains, everything, right? So you have to find it yourself. I make everything clear in NPN transistors. Now comes to the small signal model.